Welcome to Module 5. This module topics are correlation and regression. Just to give you a quick overview, correlation and regressions are advanced topics. So especially regression, there are a lot of calculations, very advanced calculations, so things might get a little complicated for regression in particular. And regression and correlation is something that you just cannot cover in one module, so it's packed in one module this week. And so if you get a little bit overwhelmed with regression, that's understandable. So I recommend you take the time to go through my spreadsheet and the PDF file that I'm going to show it to you, and to take the time to understand the concepts behind them, and not worry too much about the calculations, because there you will be doing the calculations in Excel, and there are a lot of advanced things that I'm just gonna say, okay, just trust the calculation, the spreadsheet, and to do your calculations. So as usual, if you have any questions, just let me know. But just letting you know that these are hard topics. So if you have a difficult time understanding, that's understandable. So take your time, and then things will be clear. So before you do Module 5 problems, I recommend you go to my website and then read the PDF that I prepare for you. It'll give you a quick overview on what's regression, what's correlation, and where things come from. It's just light reading. So I recommend you do that. I'm going to focus on how to do calculations and how to use a spreadsheet so that you can get the right answers. Okay, so read the PDF first and then go to my spreadsheet, which is right here. Before you use a spreadsheet, here's one thing you need to do is that if you go to the data file or data tab on your spreadsheet, you should see this data analysis button here. If you do not, follow the directions here to add this button to your copy of the spreadsheet. So this should work for 2010, 2013, and 2016. We'll be using this button to do calculations a little bit later on. All right. So let's move on to regression, correlation first. Here's an example. Given the data here, the different car types, and then the weight data, and then break-in distance data, find the correlation coefficient, which is represented by R. So if you see R, that's asking for correlation coefficient. And calculate R squared, basically the square of the correlation coefficient. We'll talk about that in a little bit. And determine whether there is sufficient evidence to support the correlation between the weight of the car and then break-in distance at alpha is equal to 0.05. So it looks like it's a hypothesis testing, and it is. So we'll be using correlation to do test a claim of a correlation. So here's the data. First thing was asked was to figure out the correlation coefficient. So that's R, and there's a function for that, CORREL, in Excel. This reproduces this formula for if you were to do this by hand, correlation coefficient by hand. Here's what you gotta do. And as you can see, it's very complicated. One of the most complicated formulas you've seen in statistics. So if you've been doing calculations by hand, this is the time you use Excel to do the calculation, because this will take pages and pages just to calculate one correlation coefficient number. Fortunately, we have Excel to do this for us. So here's how you do it. Equal sign, CORREL, and select the first variable, which is this, comma, and then choose the second variable, close parentheses, press enter, and you get negative 0.087. That's your correlation coefficient. So square this by doing this and 2, so shift 6 2, and then you get R squared. By the way, this R squared is also known as coefficient of determination. So if you're asked to figure out the coefficient of determination, first you have to figure out the correlation coefficient, and then square that. So that in this case it's going to be 0.0075. Okay. So that's number one. So determine whether there's sufficient evidence to support the correlation between the weight of the car and then braking distance at alpha is 0.05. So how do we do that? Here's the rule. If the R, the correlative coefficient, the absolute value of that is bigger than critical value, which we'll get to in a little bit, if R is bigger than critical value, you reject the null hypothesis. Okay? If the R value is less than critical value, then you fail to reject the null hypothesis. So we'll be using the critical value method to make a determination as to do we reject the null hypothesis or not reject the null hypothesis. So this table A6, that's in your book, but I have it reproduced here in this tab. So you have this for your reference. So you have to pick the n and the alpha, which is given as 0.05 and 0.01 here. So if you count the number of cars in here, there's 32 of them. Okay, so when you go to the table R or table A6, you pick the n that's closest to your given problem. So in this case, you pick 30. And under alpha of 0.05, you get 0.361. So that's going to be your critical value. Okay. So you compare the critical value of 0.361 to 0.087. So one thing you have to do is if they have opposite signs, just make them the same signs. So let's make this both positive, positive 0.361 and then positive 0.087. You compare the two. You see that the correlation coefficient is less than the critical value of 0.361. Okay, this is smaller than this, even if when they're both positives. So what does that mean? Using this rule, since the R is less than critical value, you fail to reject the null hypothesis. Okay, so that's what this conclusion is. So what does that mean in terms of this problem? It means that we can conclude that there's not sufficient evidence to support the correlation between the weight of the car and then the braking distance. So seemingly it doesn't matter what the weight of the car, it doesn't affect the braking distance according to the data provided here. Okay. One thing you should be able to do is to create a scatter plot like this. Because if you do the reading, oops, not here, in the lecture notes, one way to explore data is to plot scatter plot like this. So in this case, it is considered to be positive correlation if you create a scatter plot of the data, two variables. This is considered to be positive correlation because in algebra it's defined to be a positive slope if the slope goes from bottom left to upper right. So this is a positive correlation. Similarly, this is a negative correlation because it goes from upper left to bottom right. And if you took algebra, you know this is a negative slope. In this case, if it's just scattered with no pattern, then it's considered to be no correlation. Correlation coefficient be 0. And one more relationship you might see is it's called nonlinear relationship, where linear means it's going to be a straight line. In this case, it's not. If it's curved, then it's considered to be nonlinear. So this is considered to be nonlinear relationship. We are not going to cover this. We are only going to look at linear relationship or correlation, which is either positive, negative, or there isn't any. So in order to look at correlation, we look at the scatter plot. So you have to recreate something like this. So how do we do that? Okay, so to do so, go to Insert, Charts, and then scatter plot, you're gonna do the first one. Okay, so to do so, select both variables, insert scatter plot, the first one. Okay, it looks like this. And we want it to look like this, so we're gonna have to do some modification. So change the title to say scatter plot, because we're not really looking at the break-in itself. We're just looking at the correlation between weight and break-in, so that's not the correct title. So here we go. You notice that this is kind of bunched together to the right. There's nothing going on between, say, 0 to 2000, 2500 or so. So we don't need this blank space, so let's get rid of it. So to do so, just double click on this bottom axis, and you see minimum here it is 0. Just eyeballing it. Let's make it 2000. Enter. And then it gets rid of this blank space here, so it's more spread out. Okay. Two more things you have to be able to do is that to create this line, it's called a best fit line. So we want to see what the trend is. And the other thing you're gonna have to learn, is that have Excel create this equation here, and then this R square. See, Excel can calculate the R square value for you. So let's have these two things done for us. So to do so, double click on one of those dots, and let's see, did I do it wrong? Let's see. Oh yeah, sorry. Click on it and then right click and add trend line. That's how you do it. Okay, so let me do it again. Click on one of the dots, right click it, and say add trend line. That will give you the trend line here. And you have these options. We're only gonna do linear trend lines, so just pick linear. Okay. And then if you scroll down, you see this, it says display equation on the chart. Click on that. Display R square value on the chart. Click on that. Close it. And you see that it's overlapping, but it's right here. So if you like, you can make it bigger. Now it matches this, and then this, and R squared. Okay, so that's how you create a scatter plot that has complete information. So you have dots, trend line, equation, and then R squared reproduced. So that's how you create the plot. Okay. If you do hypothesis testing using p-value method, here's how. Here's an example from the book. There's a shoe print length and then the height. Okay, there's correlation between these two variables. So then the claim is there's a linear correlation. Now hypothesis is that there's no linear correlation. And by the way, this P looking thing, it's pronounced rho. It's Greek letter for R. And for this hypothesis testing, we'll use the degree of freedom, which is n-2. Okay. So if you do so, here's 5 degrees of freedom is -2. This set will calculate the test statistic, which is this formula. And it will also calculate the p-value for you. You see it's two-tailed because we're doing, yes, there's a linear correlation. No, there's no linear correlation. It's 0 because if you, as you've seen earlier, if there's no correlation, R is 0. So it's either 0, 0, or not 0. Okay, so p-value in this case is 0.2937. Same rule applies. So since this is bigger than the significance level of 0.05, we failed to reject the null hypothesis. Okay. So that means there's no linear correlation between the shoe print length and the height. Okay. Here's another thing you need to know is that the correlation does not imply causality. So that's the two-tailed test. How do you do one-tailed test? Well, we're not going to get into that, but if you ever had to do that, here's how you set up the claim of a negative correlation. That rho is less than 0, which means it's going to be a left-tailed test. And if it's a positive correlation, then it's a right-tailed test. Okay. We're not going to cover that. This is just for FYI. So that's regression, or sorry, correlation. Let's move on to regression. And this is where the rather complicated calculations come into play. Well, one of the two. So the equation you saw earlier in this plot here, that's the regression equation. So Excel knows how to reproduce that. Okay, so what is that? It's the equation for this best fit line. Okay, so if you know, if you remember from algebra, if you have a straight line, you can extract a equation that's gets to that straight line, or if you have the equation here, you can produce the line here. So we can go back and forth. We do the same thing here. Okay. So if you remember from algebra, the template looks like this. Oops. Okay. Where m is the slope and b is the intercept, x the independent variable, and y is the dependent variable. Okay. So we have something similar to that in regression. So this is a template for regression equation. B0 stands for the intercept, and then B1 stands for the slope. So it's flip-flopped. Okay. It's y hat here because it's called the predictive value. So that's something we calculate. So that's why we have a y hat here. So in order to get the regression equation, your job is to figure out B1 and then B0. So if you were to do this by hand, here's a slope. R of sy divided by s. And then intercept is y bar minus b1 times x bar. Okay, we're not going to use this. We're going to be using Excel to do this. So if you're following the lecture notes, here, here's an example in the lecture notes. So I'm going to reproduce this here. Okay. We use regression to make a prediction. So given the data, we want to make a prediction. So looking at this example, we want to use the explanatory variable x, the shoe print length, to predict the responsive variable y. So given the shoe print length, we want to predict the height of a person. So here's the data we have. Okay. So R here, as we calculated in the last tab. So how do you calculate the slope, which is B1? We use the slope function, which is slope. Select y's first, oops, comma, and then x. Okay, so don't do it backwards. Y first, x first. And then for the intercept, guess what? The function name is intercepts. So you do the exact same thing you did for the slope, except you use the intercept function. Okay. So if you combine the two, you get y hat is equal to 125 plus 1.73x. So if you're asked to provide the regression equation, here's an example how to do that. You have to manually type it up. Okay. You already know how to figure out the scatter plot, so I'll leave it as is. So if you're asked to figure out the regression equation, here's one. Okay. So now the question is, how do you make predictions? Well, there's a process to that, and this is what it is. First, you determine if the regression equation is a good model. So you first figure out the regression equation, and the next step is this a good model? Yes or no. If it is yes, we'll use it. If not, we have alternative. Okay. If you determine the regression equation is a good model, that means that there's significant linear correlation. You use the y hat, which is this. So basically, use this regression equations to make the prediction, which is y hat. Okay. If you determine the regression equation is not a good model, sometimes you find that way. If that's the case, you use y bar, which is similar to x bar, meaning it's the average of the y's. Okay, so what I'm saying is that if you determine this regression equation to be a good model, use this regression equation to figure out whatever the necessary y bar or y hat is. If you determine this not to be a not good model, then what you do is just take the average of these numbers here. So let's look at an example. Okay. So we first determine regression or the correlation coefficient to be this 0.5913, and we look at the table. Okay, here 0.878 or 0.959. So let's look at both for the time being. Compare these two numbers with 0.591. Okay, so here's the reproduction. You see that the R, regardless of the alpha 0.05 or 0.01, you see that the 0.591 is less than 0.87 or 0.959. Okay, so according to the rule we just learned, there is no correlation. If that's the case, then we determine that the regression equation is not a good model. Okay. So in your problems, there won't be a case where it's going to be in between. So it's not going to be something like 0.950 or something like that. Okay, so it's either going to be smaller than either of these two or bigger than these two. So don't worry about the situation where it might be somewhere in between. You will not see that. That's just a side note. So since regression equation is not a good model, we use the mean of the y's to figure out the predicted value of y. Okay, if that's the case, you take the average. So I'm taking the average of these numbers. Okay, right here. So you just use the average function to figure out the predicted value. Okay. If you're going to do advanced regression analysis, you can use the forecast function to make a single prediction or trend function to make multiple predictions, should you ever need to use regression. Those are the functions you might want to learn. Alright, so that's when the regression equations is not a good model. What about the case when it is a good model? So how do we use that? Let's look at another example. The scatter plot and regression equation are shown for 40 pairs of shoe print lengths and heights. Predict the height of the person whose shoe print length is 29 centimeters, and if the correlation coefficient is 0.813. So this problem has done a lot of work for you already. Here's a regression equation, and then here's a correlation coefficient. So let's determine whether this equation is a good model or not. Okay, so we take the R is 8.13 and go into here to see what that is. So 40, 0.312 and 0.402. You see that the 0.813 is bigger than either one of them. And if you do p-value method, you see the p-value is going to be practically 0. So that suggests that this equation is a good model, so we can use this. So how do we use that? Well, we basically substitute x with the given number. So in this case, 29 centimeters. So we're going to be doing 80.9 plus 3.22 times 29 centimeters manually. Okay, so 29 centimeters. What's y hat? 80.9 plus 3.22 times C108, which is same as 29. So for predictions, you have to do a manual calculation in Excel. Okay, so there's no function for that. So here's how you do the y hat predictive value with a good model, not a good model. Okay. Let's look at the outliers and influential points. Okay. Most of the time, the data points are within close proximity of each other. But sometimes it's not, like for example, like here. This is considered to be outlier because they're not close to this trend line. So how do we accommodate that? Here is the definition, outlier and influential points. Okay. So let's see if another point, additional data point, say x is 35 and y is 25 centimeters. Is this an outlier? Is this an influential point? Let's see that. The way you do that is, it's a little subjective, but let's say without this additional data, the plot looks like this. Okay. With the addition of this 35 and 25 centimeters over here, you see that it's two things. It's way out here. That makes this point an outlier, and the slope changed dramatically. It was positive, but it's slightly negative here. If that happens, then you can say this point is an influential point. So in order to determine whether something is influential and or outlier, you have to create another plot. Okay, so how do we do that? Basically, up here, and it's 35 and 25, so add 35 here, 25 here, and just make another plot. Okay, and then create a trend line. Okay. Yep. You see that originally it was positive, but with the additional point, it's negative. So I can say this is an influential point as well as an outlier. Okay, so that's how you determine if something is an outlier and or influential point. You just have to create a second plot and make a comparison. Okay. Let's move on to prediction intervals. So prediction intervals are similar to confidence intervals that you've been seeing. The prediction interval is an interval estimate of a predicted value of y. Okay, so instead of looking at the parameters like the proportion and the mean or the chi-square or the standard deviation, we look at the interval estimates for the variables, and that's called the prediction interval. So that's the difference between the two. Okay. Similar to confidence intervals, you have prediction interval, which looks like this: y hat minus e, y hat plus e, e being the margin of error. This is the formula for margin of error. We use t, n, x0, x bar, and x's. And there's another additional variable you have to calculate, which is called the s of e. And the formula for that is this. I'm just going to tell you that calculating e is very time consuming and difficult and time consuming, because not only you have to do the square root part, you have to do this as well. So do not try to compute E or SE by hand. You're never gonna finish. Okay, so I'm gonna show you how to do these in Excel right now. There's an easy way to do S of E anyway. So if you read through the lecture notes, there's an example that does something similar to this. If you use 40 pairs of shoe length and heights, construct a 95% prediction interval for the height, given that the shoe print length is 29 centimeters. Okay, so here's the process. I'm just going to show it to you. You don't have to actually do this. The steps are, first, you have to figure out the regression equation, which I shown it to you. By the way, the data is over here. Okay, so there are 40 of them, 40 pairs. You first figure out the regression equation, same steps we just did. What's x of 0? That's given to us 29 centimeters. We then calculate the S of E, which I'll show you in a later in the lecture. And you figure out the predictive value here using this regression equation. Confidence level is 90% because according to table 8.1 we're doing where'd it go? Anyway, table 8.1, look at table 1 and we get 90%. N is 40, degrees of freedom is 2 minus that, and T is this. So if you do all these calculations, you get a margin of error this, which reproduces all these things. And if you have margin of error, you use this and then this to have the prediction interval. So 174 minus 12, 174 plus 12, essentially. So if you have a E and if you have a Y hat, you can figure out the prediction interval. Like so down here. Okay. Once you get that, the conclusion is the same, that this means that we are 90% confident that the interval 162.1 to 186.5 contains the height of 174.3 when the shoe print length measures 29 centimeters. Okay, so 174.3 seems to be a reasonable prediction. Okay. That's a lot. But basically, have Y hat, have margin of error, then you can get the prediction interval. Alright. Moving on to variation. Okay, so read this. Okay. And we're going to be covering the explained variation and the unexplained variation. So, going back to the spreadsheet, we want to know the R squared, which is the coefficient of determination we saw earlier, because it's a ratio between the explained variation and then the total variation. Okay, so what percentage of a explained variation is out of total variation? So Excel can figure out the R squared, and I'll show you how to create this table a little bit. But once you get the table, you look at the column that says R squared. In this case, it's 0.6608884, so roughly 66.1%. So that means, given this information, we can say that we conclude that the 66.1% of the total variation in height can be explained by shoe print length. The other 33.9%, we don't know what it is, what influence it has. But we know that roughly 66% of it comes from the shoe print length. Okay. Here's just FYI. Total variation is the summation of the explained variations and unexplained variations. So if you add them together, you get the total. The calculate variations is a pain. Well, if you do it by hand, but here's how you do it by hand, or manually. The consumer price index and the cost of a slice of pizza in New York are listed below. Find the explained variation, unexplained variation, and a total variation. So if this table can handle up to 7 variables, so here's 5, here's 5. If you enter the correct numbers, this part of the spreadsheet will calculate the explained, unexplained, and total variation for you. Okay? But instead of doing that, we're going to use the built-in function in an Excel to figure out these numbers, as well as this table right here. So let me show you how to do that right now. Okay, so here are the steps. Go to the Data tab, find this button, click on it, and make a selection, regression. Okay. So input Y range. Here you go. Input X range. Here you go. Labels, I included the labels, so it's here. And I'm going to output it to a new worksheet. Boom. There it goes. Okay. So I have a prettier version here, so I'm going to look at here. You notice that the R-square values is here. So 0.97 is the R-square. That's pretty high. So 97% of variation can be explained by CPI. Okay. Here's the explained variation. Here's the unexplained variation. And this is the total variation. So if you ask for variation, just look at this column, SSM column, and you have the answer. Okay. So you can do it by hand, or let Excel do it for you. You get the same answers. So that's how you calculate variations. All right. That was a lot of information. So let me review it by going through an example problem similar to the homework assignment. Okay. So the pair below consists of test scores and hours of preparation for 5 randomly selected students. Here you go. So let's calculate the correlation coefficient. Correl. Select this, comma this. You get this number. Intercept, y's, comma x's, and then slope. Okay, easy peasy. So what's your regression equation? This. 47 plus 3x. Let's recreate this scatter plot. Select all these. Insert. Plot. This plot. Okay. Oops. Let me redo. I made a mistake here. There you go. Redo. Okay. Insert. There you go. So change it to say scatter plot. click on one button, right click, add trend line, linear, add equation, and r squared. Okay, if it's too small, just make it bigger. Here. You see the equation matches our equation. And if you square this, you get this, 0.9406. Okay. Moving on, so that you have to be able to create the scatter plot. Is this a good model, yes or no? So there are 5 of them. Let's look at the table. 0.878, 0.959. You see that it's bigger than either one. Well, assuming the alpha is 0.05, we compare to 0.878, so that's bigger. So yes, this equation is a good model. If that's the case, we'll use this to make prediction. So assuming 10 hours of study, what is the predicted score? So basically 10 times 3 plus 47. Okay. You do that manually. Sometimes the predicted score might go over 100. Let's say like 110 or so. Then you can leave it as 110, or more realistically, the upper limit is 100. So you say 100 points if should that happen. The assignment asks for SOV, so let's figure that out. Okay, by doing this, by reproducing this table right here. Okay, so again, data analysis, regression. Okay, what's the Y range? We want it to be here, comma, oops, not comma. X range is here, enter. And for the example here, I'm just gonna output out to here. You don't have to, you can do whatever you like. But, okay. Oops. No. Let's see if this works. No. Alright. It's giving me issues, so I'm just gonna go to new sheets. Yeah. Oh. Okay, this is not working out as smooth as I hoped, but fear not, I'll get to it. Okay. Okay. Anyway, here's the output, r squared, and then these numbers, but I have it reproduced in the same worksheet, so let's reference here. So SOV will be this, 3.559. If the question asks for explained, unexplained, and total variation, here's unexplained. Sorry, that's explained, unexplained, total variation. Okay. So given the margin of error is E, give the 95% prediction interval for somebody who studies 10 hours. Okay. So in order to do that, you need the predicted value of y hat, which we did it up here. It's going to be 77. So it's going to be 77 minus 35, and then 77 plus 35. So this is what I was saying, that the range, even the upper limit could be beyond the practical value. So in this case, the interval will be 42 to 100. We already covered the variation. And R square is here. Okay. And that's all there is to it for this kind of problem. Okay, so now you are able to do the assignment and the quiz, which I recommend you do after you practice with my spreadsheet. Okay. And for the project phase, it says to submit your final draft, but I'm having you not do this because since you already turned it in to module 4, in the draft in module 4, and then if I give you feedback and if you turn it into module 5, your module 5 phase 5 the paper will be gonna be 100% anyway, so that's kind of pointless to have you submit something that's going to be 100%. So you don't have to do project 5. I'll just give you the grade that matches your overall grade. So this project phase 5, so that it won't impact your grade in either way, positive or negative. So you don't have to do it, but you still have to turn in something for this course project. So basically, resubmit your module 4 phase 4 paper, or just submit something blank so that I have a space to give you a score. So you don't have to do it, but you still have to turn in something so that I can give you a grade for phase 5. If you have any questions about that, let me know, but that's what you need to do. Okay, so that's it for module 5. So I recommend you read the PDF first, practice with the spreadsheet, make sure you can get the right calculations, and you try the assignment before you do the quiz. Okay. Have a good week. I'll see you next week.